Mars has 700 times less atmosphere than Earth, not a little less, not thin, 700 times. At the surface, the pressure is roughly what you'd find at 35 kilometers above Earth, above weather, above clouds, above the layer where aircraft can fly. You cannot stand on Mars without a pressure suit and survive longer than it takes to lose consciousness. The air is there. It just isn't enough to be air in any sense that matters to a human body. That is the planet today. "4 billion years ago, Mars had rivers. Not channels carved by brief catastrophic floods, though those existed too. Rivers, networks of them, running for millions of years, fed by rainfall, pooling into lakes, possibly feeding an ocean that covered the northern hemisphere to a depth that researchers at the United States Geological Survey have estimated at over a mile. Mike Carr spent decades mapping those features from orbit. On a Tuesday in February of 1995, looking at drainage patterns in the southern highlands, he set down his notes and wrote that what he was seeing was indistinguishable from terrestrial river valleys. The same branching, the same gradient, the same structure you'd find in any river basin on Earth. The water was real. The atmosphere that sustained it was real. The pressure at the Martian surface 4 billion years ago was likely comparable to what you'd find at sea level on Earth today. That planet is gone. November of 2014. A spacecraft the size of a school bus fires its engine and drops into Martian orbit after 10 months in transit. Bruce Jakosky, a planetary scientist at the University of Colorado in Boulder, has been building toward this moment for years. The Mars Atmosphere and Volatile Evolution spacecraft is designed to do one thing: measure, in real time, the rate at which Mars is losing its atmosphere right now and work backward from that number to reconstruct the full history of the loss. The instruments track individual ions, electrically charged particles of oxygen, carbon dioxide, nitrogen, as they are stripped from the upper atmosphere and carried away by the solar wind. Not an average over geological time, an actual count per second of atoms leaving the planet. What Jakosky's team found in the first year of observations: Mars loses roughly 100 grams of atmosphere per second to space. Over 4 billion years, at rates far higher when the early sun was more active, that accounts for the entire atmosphere. The mineral record in those ancient valley walls tells a specific story. Phyllosilicates, clay minerals that only form in the sustained presence of liquid water, are embedded in rock layers dating to more than 3.5 billion years ago. Not traces. Thick deposits spread across thousands of kilometers of the southern highlands. Bethany Ehlman at the California Institute of Technology mapped their distribution from orbit and found the same pattern repeating: clays forming in riverbeds, in lake beds, in deltas where rivers once emptied into standing water. She published those findings in 2011. The water was not a brief episode. It was a regime. The atmosphere that made that water possible had a pressure somewhere between half and twice what we breathe on Earth today. That is the planet that existed. It is not the planet now. There is something I cannot fully name about what that timeline does to me. Not the scale of it. The scale is just numbers. It is the ordinariness. 4 billion years ago, there were rivers on Mars, and then there weren't, and the mechanism that ended them was nothing more dramatic than a planet being a particular size. I don't know where to place that. I'm not sure the category exists yet. Jakosky's instruments have been running for 3 months when Jasper Halekas, a physicist at the University of Iowa who joined the mission to analyze the escape pathways, sits down with the first full data set. He is in his office in Iowa City, and what he is looking at is a map of the regions above Mars where atmospheric particles are being accelerated to escape velocity and flung into space. He describes the boundary where this happens as something like a wound that never closes. The atmosphere bleeds. Slowly now. Fast then. Ultraviolet radiation from the sun strikes the upper atmosphere and ionizes molecules, knocks electrons loose, leaving positively charged ions. On a magnetically protected planet, those ions are trapped and eventually return to the lower atmosphere. On Mars, after the magnetic field collapsed, the solar wind, moving at 400 kilometers per second, encountered those ions directly. The interaction created an electric field that threw them outward. Not all of them, not instantly, but continuously, without interruption, for 4 billion years. Carbon dioxide went first, in bulk, then water vapor. The greenhouse effect that had kept the surface warm enough for liquid water began to fail. Temperatures fell. The remaining liquid water froze or evaporated into a thinning sky. The sky itself continued to thin. This took hundreds of millions of years. In geological terms, it was not slow. The magnetic field collapsed because the core cooled. Dave Stegman, a geophysicist at the Scripps Institution of Oceanography, runs thermal evolution models of planetary interiors. One afternoon, he pulled up a simulation of the Martian core cooling through the first billion years of solar system history and watched the convection patterns slow, fragment, and stop. What his models show is this: Mars is smaller than Earth, roughly half the diameter, about 1/10 the mass. A smaller body radiates heat into space faster relative to its size. The liquid iron in the Martian outer core, which had been churning in the patterns that generate a magnetic dynamo, gradually stopped moving as the temperature dropped. What killed it was not a catastrophe. It was physics applied to a body that was simply too small to hold its heat long enough. The size was the sentence. Consider for a moment what you are. You are standing on a planet that has had a magnetic field for 4.5 billion years. That field has never stopped. Every generation of life that has ever existed on this planet, every organism, every cell, every moment of biology happened inside that invisible structure. We did not inherit a habitable world. We inherited a field that made it one. The difference between our history and Mars's history is not intelligence or luck or position in the solar system. It is that the thing generating our field has not yet cooled enough to stop. Francis Nimmo at the University of California, Santa Cruz analyzed the magnetism preserved in ancient Martian rocks. On a specific afternoon in 2009, working through the crater density data used to date the youngest magnetized formations, he arrived at a number. The Martian dynamo shut down somewhere between 3.9 and 4 billion years ago. Not a range chosen for convenience. A constraint extracted from the physical evidence, tight enough to say, within a few 100 million years of the planet's formation, it was already dying. The fossil magnetism in different ancient regions points in different directions. The dynamo was unstable, reversing, flickering, before it went dark for good. Some water did not leave. It went down, not up. In 2018, Roberto Arose, sitting in his office at the National Institute of Astrophysics in Bologna and reviewing radar return data from the South Polar region, found a reflection pattern roughly 20 kilometers across, consistent with a liquid water lake beneath the ice cap, kept liquid by the pressure above it and possibly by dissolved salts lowering the freezing point. He published the finding. Isaac Smith at York University spent the following months running the same data through alternative models. One specific evening, he found that layers of frozen carbon dioxide or certain volcanic materials could produce an identical radar signature. The debate has not been resolved. What is not debated is the ice. Vast quantities of it, locked in permafrost, in polar caps, in subsurface deposits that future missions will spend decades mapping. The water did not all escape, it was sequestered. Mars is not dry. Mars is frozen and airless. The distinction matters if you are trying to understand what might have survived there before the atmosphere was gone. The difference between Mars and Earth is not a story about one planet being lucky. It is a story about mass and about what mass determines. Earth's core is larger. It has stayed liquid longer. The churning of liquid iron in our outer core generates the magnetic field that extends tens of thousands of kilometers into space and deflects the solar wind before it can reach the upper atmosphere. That field is the reason our atmosphere has been here for 4.5 billion years. It is the reason you are here. Mars had that field once. It lost it because the core cooled. The core cooled because the planet was too small. The planet was too small because of where it formed and what material happened to aggregate at that distance from the early sun. The difference at the bottom is a number, a mass ratio. One planet had enough, the other didn't, and the result is a living world and a dead one separated by a number that no one chose. Mars is not a warning about what we might do. It is a measurement of what mass does, given enough time. I have no uncertainty about this. What I have uncertainty about is what it means to live on the planet that hasn't run out yet, and to know with the precision we now have exactly what running out looks like. Earth's magnetic field is not permanent. Nicolas Gillet, a geophysicist at the University of Grenoble, was reviewing outputs from the European Space Agency's Swarm constellation on a morning in 2022 when he looked at the latest data on the South Atlantic anomaly and found he could not extract from it a timeline. The field has weakened by roughly 9% over the last 150 years. The anomaly is real and drifting westward. Whether it leads to a reversal, the north and south magnetic poles swapping positions over thousands of years, or recovers, the data does not say. The field does not operate on a clock. It operates on the thermal and chemical state of the core, which we cannot observe directly and can only infer from seismology and from the behavior of the field itself. The last reversal was approximately 780,000 years ago. Gillet closed his laptop that morning with a number in his head, 9%, and no way to tell whether it was noise or a trend or the beginning of something the geological record had seen before. That is the precise location of the boundary, not a gap in the data, not a failure of instruments. The boundary is in the physics. The process generating the field happens at depths and pressures that no instrument has ever reached, and the surface signal is all we have. The field is still here. We don't know for how long or